Welcome to Brain Vision.
I want to obtain a formula for the mass of the ion. I have provided an illustration that shows this problem. So at point A, the ion starts off from rest and begins to accelerate through the potential difference V, where it then enters the magnetic field at point B. At point A, since it starts off from rest, the ion will only have an electric potential energy, which is given by its charge Q multiplied by the electric potential difference V. At point B, the ion will have completely accelerated through the potential difference and acquired a maximum kinetic energy given by 1/2 times the mass times the velocity squared, the velocity we will call u, where it then enters the magnetic field and travels along a circular path with radius r. Now, by the conservation of energy, the potential energy at A and the kinetic energy at B must be equal. So we can set these equal, and we can then obtain an equation for the velocity u, which we will need for this derivation. So if we multiply both sides by 2 in this equation, and we divide both sides by m, we can then get u squared by itself. And so we'll do that real quick here. And we see that u squared is equal to 2qv over m, and u is equal to the square root of 2qv over m. Now, when the ion enters the magnetic field, a magnetic force, acts on the ion given by the charge times the velocity of the ion times the magnetic field strength. This magnetic force only changes the direction of the ion's velocity, but not its magnitude. And this is the only force acting on the ion. But since the ion is moving along a circular path, this must also be equal to the centripetal force by Newton's second law of the circular motion. And this is given by the mass times the square of the velocity divided by the radius of the circular path. And we can further simplify here by dividing by u, which then gives us qb is equaling mu over r. And so now we have two equations we can use. If we insert the square root expression for the velocity into this qb expression right here, we then have qb is equaling m over r over the square root of 2qv over m, which further simplifies as 2mqv over r. There was a partial cancellation of the mass right here. So now we continue, and we can multiply both sides here by the radius. And we see there's a cancellation. And now we can square both sides of this equation to get q squared b squared r squared is equal to 2mqv. And now we can divide both sides by the charge. So we can, and for that matter, we can really divide both sides of this equation by 2 times the charge times the potential difference. And this will allow us to get the formula for the mass that we want. And so we have here q times b squared times r squared over 2v is equal to m. And this is the formula that we want. So now we move on to the next part of the problem. And we know that the radius is 50 centimeters, which is really just 0.5 meters. 50 centimeters is half a meter. We know the magnetic field is 0.15 Tesla, and the charge is the usual value of 1.6 times 10 to the minus 19 coulomb. And our assumption to be made is that we're working in atomic mass units for the carbon-12 ion. And we're going to neglect the mass of the electron and just assume that the carbon-12 ion is 12 atomic mass units. So what we can do for this problem then, this second part of the problem, is just rearrange the mass formula that we obtained to get a formula for the voltage that we need. So if we start here with the mass formula that we just obtained, we can write it as before QB squared R squared over 2V, and we can literally just multiply both sides by voltage and divide both sides by mass. This way we just rearrange it, and this gives us the voltage is equaling, and I'm just illustrating the cancellation here, the voltage is equal to the charge times the square of magnetic field and square of radius over twice the mass. Now we're going to substitute our numerical values into this formula up here, and I'll just start up here and we'll do so. So we have 1.6 times 10 to the minus 19 times 0.15 squared times 0.5 squared over twice the mass. But remember, we need 12 atomic mass units for carbon-12, so there's a factor of 12 right here. So we have 1.66 times 10 to the minus 27 kilograms, because we want to work also in SI units. So now when you work this out, you obtain 22,590 volts. And you can write that in kilovolts, which is 22.59 kilovolts. And this expression for the voltage will be useful in the next part of our problem, and you could use it to rearrange for that part as well. So now we come to the last part of our problem, and that is to talk about the beam separation. If we have two different isotopes, carbon-14 and carbon-12, can we detect the separation of the beams in our detector, which is the gray rectangle in the illustration? So now what we do is we can start with the voltage equation, and we can rearrange it to get an equation for the radius. And what we're essentially going to be doing is looking for a difference in radius for the two isotopes, or basically the two types of ions. And so the first thing you could do here is multiply both sides as follows. So if we go ahead and invert the factors that multiply the radius squared, that's the square of the magnetic field, then we would have the following equation that we derive for the radius. And looking at this this illustration, really to measure a beam separation, we need to look at twice the radius. Since we're looking at a whole semicircle, really the ions travel an entire semicircle diameter, not just one radius. So we want to look at a difference in radius times 2. So what I'm going to do here is write a factor of 2 times what I call delta R, which is the difference in radius. And if we're talking about carbon-14 and carbon-12, I'm going to label their mass, the masses of these ions, in terms of those ions. And that's going to be written like this: mass of carbon-14 And we have to remember, if I put a bracket like this, we need this factor of 2 here. We cannot forget that. And I'm going to put a 2 times the mass carbon 12, voltage, and charge. They have the same charge. They're simply different isotopes. Put a square root. I'm going to substitute the numbers, and we can do that on this next page. This may take a few minutes, but basically the way that works is we'll just write it here, and we have 2 times 14 times the atomic mass unit once again times 10 to the minus 27 times the voltage in volts instead of kilovolts divided by the charge times the square of the magnetic field. And I'm going to write the second term down here. Remember, this has to have a square root on it. Okay, it's just hard to write this sometimes, but anyway, 2 times 12. And again, you can't forget the atomic masses of these ions. Okay, almost there. Square root over this. And the formula, or rather the answer you get, is 8.02 centimeters. So yes, this is a detectable difference in the beam separation.